The distance travelled by a vehicle changes according to the equation s equals ut plus a half at squared, where u is the initial speed, t is the time in seconds, a is the acceleration, and s is the total distance travelled. If the vehicle started from zero and accelerated at 2 meters per second, how far has it travelled after 10 seconds? What speed was it going at exactly 10 seconds? Hello, and welcome to lesson 7. If you've made it this far, congratulations. We've made it over the hump. We've dealt with the most difficult bits. Now we can get to enjoy using what we have now learned. We don't have to try and derive the derivatives of polynomials from scratch anymore. We can just go straight ahead and use them. And this is an example of how a question on derivatives might appear, perhaps in a physics exam or a maths exam. Okay, so the first part of the question is how far has the vehicle travelled in 10 seconds? We're already given the formula. S is distance, is equal to the initial speed, which is u, multiplied by time, plus a half of acceleration times time squared. And that gives us our distance. Alright, so all we have to do is plug in our numbers. We know that the initial speed is 0, so s is equal to 0 times time, which is 10 seconds. Well, quite honestly, let's ignore that, because 0 times anything is 0, and 0 plus anything is itself. So the ut part of the equation disappears. So that leaves us with a half times the acceleration, which is 2 meters per second. I'm going to write it as 2 meters times second to the power negative 2, which is 2 meters per second. And we're multiplying that by the time, which is 10 seconds squared. Okay, so s is equal to, well, a half times 2 is just 1, so that's 1 meters per second multiplied by 10 seconds squared, so that's 100 seconds squared, or 100 square seconds, and 100 square seconds multiplied by 1 meter per square second will just be 100. So the seconds to the power minus 2 and the seconds squared cancel out, so we're just left with meters. So the vehicle has travelled 100 meters in 10 seconds. Now the second part of the question is, what speed was it going at exactly 10 seconds? Well, we haven't been given a formula to give us the speed. So we're expected to know that the distance travelled over the time taken is the speed travelled, or at least the average speed travelled. And the instantaneous speed at any given moment would be the rate of change of distance with respect to time. That is to say, the derivative of the variable s with respect to time, or ds by dt. And we know what s is. It's ut plus a half at squared. So we're looking for the derivative of ut plus a half at squared with respect to t. So the derivative of ut with respect to t is just u. And if that's not obvious, you can think that the t is t raised to the power 1. So 1 times u is u, multiplied by t raised to the power 1 minus 1. Well, 1 minus 1 is 0, so t to the power 0 is 1, so u times 1 is 1. So we've got u times 1, which is u. And then we're adding to that a half times at squared. So now the 2 is multiplied by the half to give 1. And then we've got a times the t, and now instead of raised to the power 2 it's raised to the power 1, so that's just a t. And we can say that the derivative of distance with respect to time is speed. We can't use s for speed because we've already used s for distance, so we're going to use v, even though we're not really talking about the velocity, we're talking about the speed. So v equals u plus at. Now we have our formula, we can plug the numbers in. We want to know at 10 seconds, so we're starting from 0, so that's 0 plus acceleration is 2 meters per second multiplied by time, which is 10 seconds, so that's 20, and that should be a v, not a u. I did intend to write v, I just wrote it very, very, very badly. In fact, I don't trust myself to write it well. There we go, at least that's legible. So v is equal to 2 times 10 is 20, and we have meters, and then per second multiplied by second, one of those per seconds has to disappear, so we just have meters per second, which is a good thing because meters per second is a measurement of speed. So there's our answer. The distance travelled is 100 meters, and the speed it was going when it crossed the finish line at the exact 10-second mark was 20 meters per second. So that's one application of derivatives. We can find the instantaneous speed if we're given distance. Anything where one variable changes with respect to another, derivatives are going to come in handy. Okay, well that wasn't without its charms. There's quite a nice question. But when I was answering it, I had this thought. When we were looking at the derivative of s with respect to t, we got to the ut bit, and we said that we could think of the t as t raised to the power 1, so it was 1 times u times t to the power 0, which is 1. And that all simplifies to u. So d of ut to the power 1 with respect to t is equal to u. Fair enough, but if we cast our minds back to lesson 1, when we were looking at the equation of a straight line is y equals mx plus c, we said that m is the slope of the curve of the line. So the coefficient that's multiplied by the linear term is the slope. And in fact, if we get dy by dx of mx plus c, we can look at x as x to the power 1, so that's 1 times m times x to the power 0, and x to the power 0 is 1, so that just equals m. So that's another way of looking at it. So when you see the linear term, or rather a coefficient multiplied by just a single variable not raised to any power, you can just write down the coefficient as the derivative without having to worry about all this raised to the power 1 and taking 1 off the power And the other thing is, if we take the derivative of the constant, no, we do not want to do that. Yes, we do. dc by dx, that is what we want to do. We're trying to get the derivative of the constant with respect to x. The constant does not change at all with respect to x. It's just a constant. And since the constant doesn't change with respect to x, the slope is always going to be 0. Again, we can look at it as c times x to the power 0, and then so the 0 is then multiplied by the c to make 0, and 0 multiplied by anything is 0. So you can look at it that way, but it's also good to just know that any variable that does not change with respect to what you're differentiating it to is going to be treated like a constant and will always be 0. Okay, so I thought it would be good practice to actually visualize this, so I'm actually going to put a constant into the Desmos graphing calculator. Y equals 5, and what we get is a straight line, and when I take that away it disappears. There it is. I have to zoom out to find it. So a constant, when you graph a constant, all you get is a horizontal line, a line that's parallel to the x-axis. So the slope of a constant is 0, and the slope of a straight line in the form of y equals mx plus c will always be m. That just saves you a little bit of time when you're taking the derivatives. In fact, a few other derivatives that would be interesting to note, and I'm not going to go into the details of why it is the way it is. Ask me if you want me to, and I will, but we tend not to do trigonometric identities at normal school level. That tends to be left for college and university, which is often when you might come into contact with calculus as well. So a lot of times you're expected to know your trigonometric identities, and because I'm not assuming that you know your trigonometric identities, I'm not going to go into details about how we derive the derivatives of sines and cosines, but I am going to give you them just so that you know them, because it's quite interesting. So the derivative of sine x with respect to x. If you want to know why these derivatives are the way they are, there's plenty of videos on the internet, but I can also make one if you ask me to. So the derivative of the sine x with respect to x is just the cosine of x. That's a really cool derivative to know. Another cool derivative to know is the derivative of the cosine of x with respect to x is equal to negative sine theta, or negative sine x I should say, which then comes to an even more interesting thing, that if you take the derivative of negative sine x with respect to x, well, that's actually equal to negative cos x. And the derivative, if I can find my cursor, it was hiding in the bottom of the screen, and the derivative of negative cos x with respect to x takes us back to sine x, which is a brilliant little loop. So that's a cool thing to know for your trigonometric derivatives. Okay, three more derivatives that's probably a good thing to know. If I can create a little bit of space here. Okay, so the derivative of tan x, that's your tangent, is equal to 1 over the square of the cosine of x. And then two more. This one's a great one. This is probably my favourite derivative of all because it is so very easy and easy to remember. The derivative of the exponential function e to the power x with respect to x is equal to e to the power x. It's its own derivative. The function is its own derivative. I think that's absolutely amazing. And it's really good to look up the proof of that. It's quite enjoyable. Okay, and if I can find my cursor again, here it is, hiding. The other one is that the natural logarithm is the log to base e. And we usually write it ln. So the derivative of the natural log of x with respect to x is just 1 over x. Okay, and I think that just about wraps it up for this lesson. I hope it was a lot more, a lot easier on the brain than the previous lesson, which that pre-calculus, that was hard. I understand it was hard, but once we got over that bridge from pre-calculus into calculus proper, what we're doing now is calculus proper, and the calculus proper is considerably easier, I think, than all the pre-calculus that explains why the calculus works. Okay, I hope you enjoyed that, and I'll look forward to seeing you in the next lesson.